Hello everyone and welcome to the solutions video for Codeforces round 768 or 767 or 9, whatever that is. This round was great. I was able to solve Div1 A, B and C, which is Div2 C, D, E, and was able to rank above the likes of secondthread and Costia. Okay, that's just being lucky, but I'm gonna say it, whatever. So I'm gonna be discussing the solutions for Div2 C, D, E first, and then I will go to A and B because these are what I actually coded. A and B I've just seen. Okay, so problem C, and matching. So in this problem we are given a number n, which is a power of 2, so we have something like 16, or let's say 8 for this example, and we are also given a value k between 0 to 7, which is n minus 1. And what we want to do is we want to pair, so there we have numbers 0 1 up to n minus 1, so 7, and we want to pair these numbers, so like 0 and 1 becomes a pair, 2 and 3, something like that. And then we want to take the AND of every pair, so and then I want to sum everything, and I want this value to be equals to k. Pretty random at first if you think about it, but k is in the range of 0 to n minus 1, that is the numbers. So that's what gives us the first starting point to think, and that is that can we get this value k by just one pair and all the other pairs return 0? Well, let's see. First of all, what if k is equals to 0? If k is equals to 0, we want every pair to have complementary numbers. Like if one has this, the other needs to have this, so that their AND is always 0. So let's see what the complementary numbers look like. So there will be 3 bits in 0 to 7. So 0 and its complement would be 7. Then I have 1 and its complement would be whatever this is, it's 6. Then I have 2, 0, 1, 0, its complement would be this. Then I have 0, 1, 1 and its complement would be this. These are the 8 numbers, and if we pair them like this, so 1 with 7, 0 with 7, 1 with 6, 2 with 5 and 3 with 4, we will get the AND of each of them to be 0, and 0 plus 0 plus 0 is equals to 0. Now let's say we want some value k, right? And that k is in 0 to n minus 1, so that k is one of these. The suspect is among us. Now, okay, that was a very bad joke. So let's say we want this value. So how can we get this? We can get this by pairing it with either of this or this, because they both have this bit same, right? But what happens after you pair it? After you pair it, the remaining complementary numbers, so let's say you pair this with this, then I'm gonna have to pair these two because they don't have anything to pair with, and here as you can see there is some common, and because of that common I will get something bigger than k. So I want to avoid this scenario. Now see that if you take the number which has all the bits on, so that is like n minus 1, if you pair it with k, this is k, right? You will get k in their AND, and its complement is 0 0 0. No matter what you AND with this number, you will always get 0. So you can complement it with this, AND it with this, that is pair it with this, and you will get 0 here, and the remaining pairs can stay just like usual. So what you can do is you can pair k with n minus 1, and then you can pair k complement, which is just all the bits inverted, all the relevant bits, with 0, which was the complement of n minus 1 initially, and then you can use the previously paired ones, so all the original complementary pairs. So that is a simple solution. However, there is one catch. How do you do for when k is equals to n minus 1? So when you have to do for k is equals to n minus 1, you obviously cannot pair it with n minus 1. Now this will not be possible if if n is equals to 4. If n is equals to 4, it won't be possible. Proof by input in sample. You can prove it by exhaustion or whatever that is. You can just try every possible value and you will see that you can never get that. However, for 8, can we get that? Let's see. So let's just remove this. Let's write it here. So k and n minus 1 was paired, k complement and 0 was paired, and all the remaining ones. Now let's take the other case where k is equals to n minus 1. So let's write these again. Zero one zero 1 0 1 0 1 1 1 0 0. Now you want 1 1 1. So to get that, see that if you pair it with something that has every bit on except the last bit, which would be 1. So, and that number is n minus 1 divided by 2, obviously. So this number, if you pair these two, in the sum you have 1 1 0. Now you want some pairs and to be equals to this, so that when they get added they become 1 1 1. So you look at its complement, which is this, and now you just want to fulfill its pairing, and you can pair it with actually anything. You know why? Because if you pair it, you can pair it with anything that is odd or that has the first bit, 0th bit 1. So if you, okay, let me not make it red. So if you pair this with, let's say, this, you get this, and now this is the remaining one, 0 0 0, and you can pair it with anything to get a XOR of 0. So you just pair it like this, and all the other things can get paired just like normal. So how is it generalized? See, this is n minus 1. You are pairing it with something that has every bit on except 0th bit, and then its complement would have every bit off except the 0th bit. You can do it with anything, so that can be just 3, and then its complement can be paired with 0 0 0, because 0 0 0 is universal. So with this we get a edge case solution for k equals to n minus 1 for n greater than 4. That is, pair n minus 1 with n minus 1 by 2, and pair 1 with 3, and then 3 complement with 0, and all the remaining ones. And this is exactly what I did. So let me show you. Where's my solution? Oh, this is 1630. I want 16. Yes, so here is my solution. Let's go. I hope the zoom is fine. So first of all, I have the input taken, and this is the only case where it is not possible to get the sum to be equals to k, so that is done. Now before continuing, let me remind you that this is just a construction for the solution. There can be more solutions. I have not proven that there are not other solutions, but this is something that always works, so that satisfies our requirement. Then because I want to know all the remaining pairs, And because these things that I am removing are different for different cases, what I'm doing is I'm first of all storing everything in a set, which is here, and then I will remove them from the set so that I can get the appropriate complement number. So this is for the case when, and because when k is equals to 0, there is no unique pairings like this and this, right? So if k is not 0 and also not n minus 1, because that is different, I'm pairing n minus 1 and k, removing them from the set, then pairing 0 and k complement, and then removing them from the set. However, if k was n minus 1, I'm pairing n minus 1 and n minus 1 complement. No, sorry. This is n minus 1 divided by 2 basically. I'm just removing the last bit. It is a little bit faster than dividing. And then removing them obviously. Then x and y are 1 and 3. So pairing those up, removing them, and then pairing 0 and n minus 1 complement y. And then just, okay, so the pairing is a little bit different than shown here, but you can do it this way as well. And after that, I will go through every number. If it has already been paired, it won't be in the set. So continue. I get its complement. So let's say this is my number, right? If I want its complement, it is this XOR the number. This will give me this, right? And this is n minus 1. So n minus 1 XOR I. And then I'm just having a static assert that, is it static? I don't know. That j is not in the set, just to make sure that my set is not inconsistent. And then I pair them and remove them from the set. That was the solution for Div2C. Now let's look at Div2D. This was my favorite problem of the contest. I hope I'll be able to explain it properly. So in this, we have an array, and what we can do is subarray. Okay, I forgot what this was. Any subarray, number of elements. Okay, yes, now I remember. So we have an array, A1, A2, A3, AN. And what we can do is, we can choose a range L, R. We're also given a value K. And what we want to do is, so let's say it is like this. 4, A5, A6, A7, and K is 3. So I want to divide this array into 3 parts, 3 sub-arrays, something like this maybe. And what I want here is that the number of elements that are, so for each sub-array, so first of all this, then this. So for each of these sub-array, the number of elements that are in this range has to be greater than the number of elements that were not in this range. And this condition needs to be satisfied for everything, for every sub-array. Okay, so let me just make it a little bit better. K was 3, okay. So what is the first thing we observe here? The first thing is, no matter how you divide it, right, we will have K partitions. So partition 1 is something, let me use different color. So partition 1 is something, partition 2 is something, partition 3 is something. I don't know what it is, but the frequency, I'm gonna denote it by capital F, in the range L to R has to be greater than the frequency in range minus infinity to L minus 1 union R plus 1 to infinity for every set, for every partition, for all P. This must be true. Since this is true for everything, we can sum it over every partition, and what we will get is that the total frequency, so this was for just the partition P, but if we just sum it over, because this is what we are given in the question, And if this looks too complicated to you, this value, this is just the length of partition minus whatever numbers were in this range in that partition, obviously. So if we sum it over every p, the inequality will remain, right? And okay, where is the eraser? Yeah. So if we analyze it over every partition, since fp has to be greater than fp this value, right? So let's say a1 and a3 were in L2R. This is my L2R, and a2 was not, then this partition is valid. So 2 is greater than 1. And this type of inequality need to be present for every partition. And due to that, what happens is that f for the entire array in this range, this value needs to be greater than, actually let's write it as greater than equals to this plus 1, right? It has to be greater than, so you can just say greater than equals to plus 1. So if we add it over every p, what we just get is n is the total elements L comma R, because this is the elements that are not in the range, this is the elements that are in the range, and because there are k partitions, we get k. If this is satisfied, we can actually partition it always into k partitions such that every partition can satisfy this inequality. So let me write it a little bit more cleanly. So since for every partition p, actually let me use I. So I from 1 to k, there are k partitions. The frequency for partition I in range L to R has to be greater than equals to whatever is the number of things, number of elements in this partition minus this same value again, obviously, because these will be the numbers not in the range, plus 1. And if we sum it over everything, as you can see, n sigma npi will just be n, and this will be just again this capital F, and since they are k, they will be k. This is the inequality. Okay, so now we know that for some range L to R, if this satisfies, we can say that this is a valid range to pick. Cool. But now how do we go about generating the partition value? So basically, where do we partition? That is another big question, and we will answer it right now. So let me just remove this. So every partition, so every number, if it is inside L to R range, you can imagine it to be 1, and otherwise it is -1. So let's say it's like 1, -1, let's say -1, then 1, then 1, then 1, then -1, -1, 1, something like that. Now, since it is -1, this much cannot be our partition, right? Now, -1 plus 1, it is 0. So this array is also not possible. However, once we get here, we get a valid partition, but we don't know if it is good enough to do it here or if we should do it later on. And my claim is that since we have checked this, since we have already checked that this frequency is at least k times at least k more than the remaining frequency, if I do it in such a way such that every first k minus 1 partitions have just one extra number, then the remaining part of the array will satisfy this condition. Because notice here that two elements in the range cancelled out one element not in the range, and we used So we used something from here and something from here, and we used one of here, so it became k minus 1, and then we do it again. So notice here that this is another possible place. Okay, so we keep doing this, and now once we have done it for k minus 1 partitions, so we have formed k minus 1 partitions, right? Now we just want to prove that the remaining part of the array would be valid. And why would it be valid? Because if you count everything up to here, it will be what will be this value? So whatever, so let's say you have removed x non-valid elements or whatever they are, so out of the range elements, so that means you have used x plus k minus 1 valid elements or in the range elements. Now because the in the range elements are at least k greater than the out of the range elements, we will have at least enough elements to have the remaining part of the array to be valid. And yeah, I think that explains it. So with that said, now we know that using that, if we have a valid range, that if some range of numbers satisfy this equation, we can greedily assign the segments or the partitions, and so we can do this much. Okay, so let me just erase these things, and now we know that if we have L to R that satisfies that equation we had written, n minus the frequency plus k, then we can greedily assign the partition. But now how do we find this? That is the question. So how do we find this? We can actually binary search on it, because so we know what is the frequency of every element. So elements are in of value 1 to up to n, and we know its frequency, so v1, v2, v3, vn. And since we know the frequency of everything, what we can do is, we can, let's say if we want to know from 3 to 7 what will be the sum of the frequency, we can get that by prefix sum. So we can get that by prefix sum. Okay, so we can actually try to see if we can get a valid answer for length x of this range, because we want to minimize that range length. That is a question, that is the main part of the problem. So since we want to minimize, let's see if we can do it for a particular range x. So to see if we can do it for a particular range of x, we can just iterate through this frequency array and see the range sum, if this range sum satisfies this equation. And this is possible to do in ON, because we can get a prefix sum and then get that subarray sum, and this equation is then trivially easy to write in a programming language. So we can get that, can we do it for some range, for some length x. So if we can do it for some length x, we can also find which LNR satisfied it. And if we can do it for some length x, we can obviously do it for length greater than equals to x. So that means we have to apply binary search. So from range length 1 to n, we can do binary search. We'll check, can we do, let's say first of all n by 2. If we can do n by 2, we will try in this range and then check n by 4. Otherwise we will check 3n by 2. So that was binary search plus some basic maths and a little bit of greedy. A very good question, in my opinion at least. And now let's look at the implementation. All right, so where are we? So we have n and k. We first of all take the input. This is our frequency array. This is the prefix sum of that array. And then we are going to do binary search. And this is the mid value. We have a can we do it for this mid value? If we can do it, then we set, okay, this is garbage, don't worry about it. Then we say high equals to mid minus 1, otherwise low equals to mid plus 1, trivial binary search. And every time while checking what I'm doing, first of all I'm checking if I am not able to form the range. So I'm iterating from 1 to n, but I can only iterate up to n minus mid, right? So I'm checking it here because why not? And then I'm getting the current value. So this is okay. Let me clear it all. So I'm getting the current value, which is the prefix sum. So this, I'm calculating the prefix sum, and then so CV is just f, which I had written, and then CV1 is just n minus that. And if, as you can see, this equation, if this satisfies, then I can do it. I set whatever my L and R are, and I break out of this loop, and then I go and continue the binary search. And once binary search is over, I have the L and R, and now I have to greedily generate the partition arrays, partition points. So the starting point is 0, and the sum is 0, count is 1. So this count is here 1 because I only want to first of all generate the k minus 1 partitions, and then the remaining array will be the kth partition. So since I'm starting with 1, if k was 1, I will instantly break out, and I'll just say 0 to n, or sorry, 1 to n, because then I want to move out. So count is starting from 1 because I want to make only k minus 1 partitions. So that is why this is here. And then if aj is greater than equals to, so if it is in the range, I'm treating it as +1, otherwise as a -1. And every time sum becomes greater than 0, I have found a range, I increase the count, I update the left side of the range, and then I make the sum 0 as well. So yeah, this was the greedy, this was the binary search, and this was the pre-computation. Hope this was understandable. Okay, so Div2 now. How's the system testing going? Okay, yeah, I have passed the system test. Look at me, I defeated second thread, Kostya, Hakyobo, Balakrishnan, and even Naman. I did good, I guess. Obviously, I got lucky about these 3-4 people. Actually, these 5 people. Actually, these 6. No, these 7. Actually, everyone except this guy, I guess. So, okay, Div2 and no, this is not. Where's Div2? Div2 paint the middle. This is actually very easy for a Div2, but let's see. So we have an array, so like 1 2 3 1 3 3 5 2 6 7, and everything has a color of 0 initially. What we can do is we can choose 3 elements, I, j, k, 3 indices I, j, k, such that all of them are colored 0, and ai is equals to ak. And if that is the case, then I can color j to be 1. Now I want to tell how many maximum number of points I can color. So obviously, so here, as you can see, I have 2 and 2 colored. So what I can do is, at least I can color all of these to be 1. But obviously I won't be able to color these 2 because at least just by using these 2 values, I cannot color themselves. I can only color all the values inside them. So let's consider all the endpoints. So these are basically a bunch of ranges like this, right? Something like that. And so let's look at this range. So if we have one range like this and one range like this, we can just ignore the existence of this range, because anything that this range gives us will be provided by this range. So this is not a case to worry about. How about intersecting ranges? How do we fill these up? So these are the main points, right? So while filling this using, so A, B, C, D. So using A and B, we can fill this much and this much. And using C and D, I can fill this as well. Now what remains are points B, C, A and D. I cannot obviously fill A and D, but I can maybe fill B or C. So see, if I use AB, I can fill C. However, if I use CD, I can fill B. So when I have two intersecting segments, I can fill all the elements inside the merged range except one, because I'm combining two ranges, so one point remains undone, uncolored. So that's one thing. Another thing to note here is, what if it's something like this? So there are multiple ranges. So when there are multiple ranges, you can work out that this is actually kind of useless. Why is this useless? Is because, see, this is able to color this much, and all these values can be colored just by using these two. So in a way, this is useless, and you also cannot use these points to actually color any extra point, and you will still remain at the same amount of points you can color. So that is all these except one of them. So either this or this cannot be colored. This is here. So that is it. So all we have to do is just merge these ranges, right, while keeping a track of how many proper merges are there. So why I say it proper is because this is unnecessary, so we don't worry about it. And similarly, if we had something like this, right, then this is also unnecessary, because some other range so this range intersects with it but only goes up to here. Some other range goes further while intersecting with it, so it is more beneficial. So that is why this is also not a proper merging. So we only want to count the proper merges, and then after we have all the ranges merged, right, after we have all the ranges merged, it would be something like this. We will have a bunch of detached ranges with some merges. So it is a proper merge of 2 or 3 ranges, 4 or 5, something like that. What we have to do is get all the points here, -3 or 2, sorry, and here -3, and just like that. So how do we do that in code? Well, that is pretty simple, even though I was breaking that. My bad. I'm bad at this. My submissions. Okay, 1630. Okay, let's look at my... Oh, system tests are over, and Tourist got rip. He was so close to 4,000. I'm pretty sure even the people who defeated him might be feeling bad. Why did we ruin it for him? Okay, so here I've made a segment structure. So it has LR and count, which is how many proper merges it had. This is the default and parameterized constructor. Then taking the input, creating the starting and end point of every number so that I can get the range associated with every number. Obviously, I only care about the start and end point, the first and last point of every number, because if a number occurs like this, 2, 2, 2, I don't have to take this range. I can just take this entire range. So yeah, after that, I am creating all these ranges, and if there was no range, then I cannot color anything, so I return 0. This got me WA on pretest 13. Then I sort them, and so that I can build the proper segments now. So the current segment is the first segment, and it is currently merge of 0 things. So there are basically 0 proper merges. And then we trade from 1 to M. We take out the current range. If this range is so this is the previous range, and if this new range is like somewhere here, so new L, new R. So if it is like this, then obviously I want to push the present range and then create a new range. Otherwise what I do is, so this is like L and R, right? I will have plenty of things like this. I can have something like this, right? So I will iterate as long as the starting points are less than equals to this value, because these are the ones that intersect, and I take the maximum of next R that they provide, and that next R would be the segment that I'm taking. So, and if that next R is greater than my current R, then I update it and I increase the count. And because I have gone a little bit over due to this loop, I subtract I, and then in the end I push the last segment that I was not able to process in the loop. And then for every segment I just get the number of points I can normally do and minus the number of proper merges, and that is the answer. Okay. Div2 C, D, E done. Now Div2 A and B remaining. Hopefully I can submit now. So this problem, let me go here. And submit this to see if this works. Okay, yeah, obviously this works. So what is this problem? It's very trivial, obviously. We have an array. We have two arrays actually, A1, A2. It's actually not that trivial. My bad. So, and we have another array. Now, what we are allowed to do is, for any element, for any index I, we are able to swap these two. Now we can do as many swaps as we want, and what we want to minimize is the maximum element in A multiplied by the maximum element in B. I want to minimize this product. Now, the key observation here is that whatever the global maximum is, right, whatever the value is maximum among all these elements will obviously be in either of these, because no matter which array it goes to, it will be there. So one will always be big, either this or this. So to minimize the product, we want to minimize the other array. How we will minimize? What we will do is, we will try for every index I, we will try to make array A the smallest. Okay. So if AI is A1 is greater than B1, then I will swap. So I will get a smaller value here. And then among these, all the smaller possible values, I will take the maximum, and that would give me the least product that I'll be able to get. And my implementation is, I just loop through, also please subscribe. So I just loop through the array, and so X is the maximum I'm taking in array A, and Y is the maximum I'm taking in array B. Since I'm giving the smaller one to A, I'm taking the minimum of AIBI, and for Y I'm taking the maximum, and then I just multiply them. Next problem is fun with even Subarrays. Okay, let me just check if this works. This is actually not my solution. This is this guy's solution. Wait, I got compilation error. I didn't even check it. Let me try. Oh, because I didn't have this. Okay. Let me submit. Why? Why? Oh. Okay, accepted. So this is this guy's, not Omnix. Yeah, it's his solution. Now, what I'm doing here, first of all, let me explain the problem. In this problem, we are given an array. Once again, we are always given an array. So something like this, 4, 5, 6, 7. What we can do is we can take an even length subarray, something like this, A3, 4, 5, 6. And what we do is we assign A6 to A4 and A5 to A3. So basically, the second half gets assigned to the first half. And we want to make the array equal in minimum number of operations. The key observation here is realize that the right half is being assigned to the left half. So you cannot actually reassign the last element. This will remain the same. That means we want to make everything else equals to that. Now how can we do that? Well, first of all, we can choose this and assign that. And then we can choose the double of this and assign that, then double, and so on. But this won't be optimal, because what if A6 is already equals to A7? Then we can avoid one operation. So we want to keep iterating to the right, left, and see how many are already same. So let's say till A6 are same. Now I will use one operation to make double of it equal, and then I will repeat the same thing. And let's say A3 is equal now, so I will be able to go here and then double of this. So I will cross the array and I will be done. That's what this solution is. So here, taking the input, then x is the value we are going to make everything equal to, that is an minus 1, mx is 1. What is mx? I don't know. So that's the answer. So I iterate from the right. Okay, and every time ai is equals to x, I just move to the left, and mx is just the number of values we have already covered, so that we can get by n minus I as well, or some plus minus 1. And otherwise, if it is not equal, then we use an operation to cover I to I minus mx as well, and then mx obviously gets multiplied by 2, and then I just print the answer. So that was the solution for A, B, C, D, E. Now F, I heard, was maybe doable. I don't know, I haven't even read it, but I read in the comments that maybe it was doable, so maybe I could have done it. Yeah, who am I kidding? That's not gonna happen. But it went pretty good. I was able to defeat second thread. I can clickbait that. I will clickbait that. No one's gonna stop me. So that is it. Hope you guys enjoyed. I mean, who enjoys this? Okay, maybe you do. But hope you guys enjoyed. Leave a like, subscribe, and I'll see you next time. Maybe join my Discord. It's very dead. And bye.